Hi everyone, I'm Carlo Boursier Niutta from Politecnico di Torino, and my talk is about the fatigue design through topology optimization. In particular, I will talk about two methodologies that we have integrated into the topology optimization framework for the fatigue design of components. So we all know that the presence of defects consistently affect the fatigue performance of components, and that the additive manufacturing components are characterized by a significant presence of defects. Usually in the design of additive manufacturing components through topology optimization algorithms, the influence of the defects on the fatigue response is not accounted. And usually the procedure that is followed is the one depicted here with this flowchart on the right. Only a static constraint is retained in the topology optimization problem, and when the component is produced, the defect distribution is assessed through a micro CT, and the verification is then performed. If the component is not verified, you have to redesign the component and so redo all the procedure until the verification occurs, which is not very convenient. So the goal here is to account for the fatigue strength of the components, which is affected by the presence of defects, and accordingly formulate the topology optimization problem. In particular, we use two methodologies for calculating the fatigue strength in presence of defects. The first method is the marginal probabilistic SN curve method, which describes the cumulative distribution function of the fatigue life, and this cumulative distribution function is conditioned by the defect size, which is assumed to follow a largest extreme value distribution. So according to this method, we know the defect size according to the largest extreme value distribution. We define the quantile of the curve, and we can extract, and we define the number of cycles, and from that we can extract the stress, and so the fatigue strength, the corresponding fatigue strength according to that quantile and that number of cycles. It is based on the stress gradient method within the component. In particular, the component is seen as the assembly of several uniformly stressed subvolumes. Each subvolume is subjected to a specific stress value. The larger the stress in the subvolume, the smaller the fatigue life of the subvolume according to the Pascal model. But also you add that the larger the subvolume, the smaller the fatigue life of the subvolume according to the weakest link. So this methodology allows to take into account the side effect typically seen in fatigue results. The fatigue life is modeled according to a Weibull distribution, and here again, by defining the quantile and the number of cycles, you can calculate the maximum stress, the fatigue strength of the component. For the integration of the fatigue strength within the topology optimization framework, we add the new fatigue constraint, which limits the first principal stress that is responsible for the crack propagation. Furthermore, however, you add that each iteration of the topology optimization, you add a change in the topology, which affects in turn the largest defect that you can find, and so the fatigue strength according to the first methodology. Or you had a change in the stress gradient, and so a change in the maximum strength, in the strength of the fatigue strength according to the second methodology. So we implemented an iterative procedure where we verify the discrepancy between the maximum strength retained at one iteration and the one considered in the previous iteration. And when this difference is smaller than a given epsilon value, you reach the optimal and safe design. Applied the two methodologies for the design of an engine rod made of this aluminum alloy. We considered an alpha quantile of 0.1 and the number of cycles of 10 to the 9. Here is reported the model of the engine rod. You can see in red the design domain, in gray the non-design domain. The force is applied on the upper side in correspondence of the upper shell through these blue rods, and the bottom part is constrained, fully constrained. Here I reported the marginal PSN curves obtained on hourglass and Gaussian specimens made of the same aluminum alloy. And also here I reported the PSN curves obtained with the stress gradient method on the same experimental test. So we define the alpha quantile 0.1, the number of cycles 10 to the 9, and accordingly to the two methodologies, we identified the fatigue strength. Reported the results of the optimizations. The first two topologies have been obtained with the marginal PSN curves method, while the third one is obtained with the stress gradient method. The difference between the first two is the volume retained at the end of each optimization for the calculation of the largest of the critical defect. In particular, in the first topology, we considered only the volume that is subjected to at least 90% of the maximum stress, maximum first principal stress, while in the second topology, we have considered the whole volume of the topology for the calculation of the largest defect. You can see that the final topology is very sensitive to this arbitrary choice of the volume to retain for the calculation of the largest defect. Looking at the stress gradient method, you can see that this is very similar, leads to very similar results and topology to that obtained with the marginal PSN method when the whole volume is retained, which confirms the robustness of this methodology, which do not require the defect distribution. Here on the right is also reported the loaded volumes distribution within the different optimization runs that we perform. We start from the blue distribution and we end with the red one passing through the gray ones. In conclusion, I've shown you a comparison of two methodologies for modeling the fatigue response in the fatigue life range and account the experimental scatter due to the presence of manufacturing defects. I've shown you how to implement these into the topology optimization framework and shown the application to an engine road. We have seen that the defect distribution method is strongly dependent on the choice of the retained volume, while the stress gradient approach leads to reliable results and does not require complex analysis for the assessment of the defect distribution within the component, which makes it very useful and powerful for industrial application. With this, I conclude my presentation. I thank you for the kind attention, and I also want to invite you to this special issue in Advances in Statistical Analysis of Fatigue Data, which I'm a guest editor with my colleagues, Professor Tridello and Professor Paolino. Thank you for the attention.